everyone and welcome back to this episode of Funtastic Academy. Today we'll be discussing DRAM or Dynamic Random Access Memory. DRAM is the main memory used in your computer. Whenever you want to launch a browser, play a video game, or use any other resource-intensive application, your CPU loads the data from your files into DRAM so that you can access it easier. DRAM is the memory tab you see when you open your task manager or activity monitor. But what's inside a single unit of DRAM? How does it work? How does it allow reading or writing data? We're going to answer all these questions in today's episode. This is a two-part video. So today we're discussing how a single stick of DRAM looks on the inside. And in the next episode, we'll be discussing how a stick reads and writes data. But first, let's answer the question from the previous episode. What is the unit used to measure the speed of a clock? The answer is Hertz. Hertz is named after the German Heinrich Hertz. It was originally used to measure the frequency of sound waves. So a particular sound wave might have a frequency of, let's say, 1000 Hertz or 1000 oscillations per second. In computers, it measures clock speeds. For example, the old 65CO2 microprocessor has a speed of 2 million Hertz, meaning the clock and the CPU can run 2 million operations per second. In today's high-end computers, it's obviously much faster than that. So without further ado, let's figure out how DRAM works. Let's dive in! So, you might be wondering, if DRAM is your computer's memory, then what about the registers and D-latches that we discussed in a previous video? Aren't those the computer's main memory? And come to think of it, what about the hard drives that your computer uses? That's also a type of memory. So which one is really your laptop's or desktop's memory system? Well, it depends on the situation we need. All three of them provide different use cases for reading, writing, and storing data. Drives are especially good at storing data. Your classic rotating disk hard drive or tiny solid-state drives can store information for years on end without needing any power supply. But they're very, very slow in accessing that information. Registers, on the other hand, are incredibly fast. In fact, every time your computer has to do an operation, it checks the registers. But they store very small amounts of data. You can only have a few in your system. DRAM then is the best of both worlds. It can store gigabytes of data, but it's incredibly fast. Not as fast as registers, obviously, but still it can be thousands of times faster than even the fastest solid-state drives. So, in this video, we're going to be investigating how this DRAM works, the main memory that all your applications will use while they're running. Now, what's inside a single stick of DRAM? DRAM is arranged in sticks which you insert into your computer's motherboard. Of course, if you have a laptop or phone, these are prearranged. In a desktop, you can remove them and reinsert new ones. Each stick of DRAM might contain 8 or so chips. And each chip contains bank groups of memory, which are subdivided into memory banks. Each of these memory banks stores a small amount of data, so we're only going to be looking at one of them at a time. Your stick of DRAM has some internal chips logic for deciding which memory bank you need to use when you want a specific bit of data. that comes in the first few bits of the signal you send to the DRAM to ask for reading or writing data. So, what's inside a memory bank? Well, it's a massive grid of memory cells, and each of these cells reads, writes, and stores one single bit of data. So, let's look inside one of these cells before understanding how each of these cells works in a grid to properly manage memory. This diagram that I've prepared shows exactly what's inside a DRAM memory cell. The main component that stores the information is this capacitor. If you remember from my previous videos on electronics, a capacitor is just two sheets of conductive material with an insulator in between. This means that the capacitor can store charge, kind of like a battery, but in smaller amounts. The cool thing about capacitors is that connecting a wire to the capacitor can immediately not only read the current, but also charge or discharge the capacitor. But the capacitor can't be directly connected to a wire. If it were, then we'd constantly be reading and writing to every cell in memory. We need a way to specifically select which memory cell we are reading or writing to. This is where this transistor and wordline wire comes into play. The transistor, from my previous videos, is simply a switch that allows you to connect or disconnect a wireless circuit. The gate of the transistor, or the switch, is the wordline wire. In a grid, we later show these wordline wires as being horizontal in rows. This wordline wire essentially decides whether this capacitor is active and we're doing something with it, or we're not. In this case, the charge keeps staying in the capacitor forever. It doesn't exactly stay forever though. Because this transistor is so tiny, charge can actually move across it even when the wordline wire is off. We'll discuss how the memory deals with that later when we talk about refreshing. The actual wire that we use for reading and writing data is the bitline wire. In the grid, this goes vertically. When the wordline wire is turned on, the bitline wire connects to the capacitor, and whatever charge is in the capacitor goes through the bitline wire. Then, whatever is in the bitline wire can either charge or discharge the capacitor. This might seem a bit flimsy, but when we go to the grid layout, we'll discuss how amplifiers help us deal with this. For now, just remember that these capacitor cells are read and written through this bitline wire, and this wordline wire controls whether we're reading, writing, or doing nothing at all with this capacitor. Now, let's see the grid layout on how these capacitors are actually arranged to form banks. This is a graphical representation of a single bank of memory. We have 20 cells in this diagram, 5 columns and 4 rows. In reality, there would be thousands of columns and tens of thousands of rows, but we don't need to deal with that in this diagram. Now, the bit lines go vertically. So, vertically from these wires, you read the input or output of these memories. When we're reading data, the output comes through these wires. When we're writing, we have to put the data into these. Now, horizontally come our word lines. We can turn on or off a single row of information in order to get the data from that row specifically and not any other row. Notice that we can't turn on two word lines at the same time. Otherwise, the current from both cells would come to this wire and mess everything up. You'll also notice this sense amplifier here. This sense amplifier essentially drives the voltages. If there's a tiny change downwards in this wire, the amplifier will drive it all the way down to zero. But if it goes a tiny bit upwards, it will be driven all the way to a high voltage, which in this case, let's assume is 1 volt. So, let's now discuss how reading can work using this grid. So, recap. What did we learn in today's episode? We learned how an individual cell of DRAM looks like. We learned about the hierarchy of memory and what's DRAM's place in that hierarchy. And we learned about how these DRAM cells are arranged in a grid using wordlines, bitlines, and sense amplifiers. In the next video, we'll learn about how all these components interlink together to make reading and writing data possible. Until then, I leave you with a question. DRAM generations are used the DDR format. For example, DDR1 might have been the first generation. What generation are we currently on? Tell me the answer and I'll see you on the next episode of the Funtastic Academy. Bye!